right? Difference of cubes, yeah, that's coming. Right, so right now, here's what I know. Tell me if you agree with this or not. Lambda must be 0, or x cubed minus y cubed must be 0. Right, if you factor something, right, equal to 0, zero factor property, you set each factor equal to 0. These are my two scenarios, right? Let's look at each one. I think I'm going to do them under here. Suppose lambda is 0. Right, I'm looking at each of these scenarios. Suppose lambda is 0. If lambda is 0, what does that mean? Lambda is 0, that's 0, right? Which would mean that what? Y would have to be 0. Which we already said, what? Y is not 0. So that's a contradiction. Right? You don't follow that? So, pardon?
Which one do we take ownership of? Like, do you think we should just go ahead and check for zeros and then
It really is kind of up to you. Like I said, I would have started with this, but someone had suggested like 0, so I went with that. I think no matter what, as long as you understand what's going on, there's no, I don't think there's an easy way. I mean, like when we do another one, we're going to be doing something completely different. I mean, there's not like, I don't think there's just one, like, always let the variables be 0 first. Like, at least I've never looked at it that way. I don't think it's easier one way or the other. Yes?
Even if we haven't checked the zeros in the beginning, could we have still said that lambda can't be 0 because we started with y in the denominator?
Well, we can't start with y in the denominator unless we say this, right? We couldn't have done that step unless we stated that. We had to make that. So right now, we are living under this umbrella that x and y are both not 0. And within this same thought, we're supposing lambda is 0. And we're getting a contradiction, right? This right here, if we take equation 1, it becomes y e to the xy equals 0, which is impossible, right? If lambda is 0, that's 0. That right there, we already said the left. This is not 0 since y is not 0, right? From this assumption. So what do I still have to look at then? I mean, obviously lambda can't be 0, right? So, I mean, this is drawing me to a contradiction here, right? Y'all know that's the contradiction symbol? It's two arrows hitting each other face to face like this. It's like you're drawing an arrow like that and then another arrow like this. It's a contradiction, but it really just looks like a line with an X through it. So I basically have contradicted myself because in order for this to be true, I have to let y be 0, but then I already said that y can't be 0. So what do I still need to look at? X cubed minus y cubed has to be 0, right? This is like my only hope. This is the only hope I have left, is that x cubed minus y cubed is 0. So still within this umbrella, I am now looking at this next scenario. Suppose x cubed minus y cubed. You know what? Maybe I probably should have said this in the very beginning, but now I'll state it. When I work these, I start with like a suppose, and then I make my statement. If within this idea, as I'm working this down, if within this idea I have to do another suppose, I indent that suppose, and then I work that. And that way I can keep track of where my major like conditions are, and then all these like sub-conditions within there. And then I'll restart if I have new major conditions. That makes sense? And that way everything kind of flows and looks nice. Because if you just write it like suppose, 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 you don't know when you've stopped supposing that previous suppose. Welcome to Lagrange. It's kind of weird. All right, so this right here, I could do difference of cubes, right? I could. But I think what's even better is just add y cubed to both sides. Right, just say, okay, x cubed must be y cubed. And now take the cube root on both sides. And do you have to do plus or minus when you do cube root? No. So I know here that x must be y. So I have a relationship between x and y. So if x and y are both not 0, then I know to satisfy my equations that x and y have to be the same thing. Right? Now, what are they? Well, where am I going to get that from? Third equation. If x and y are the same numbers, then I can replace that y with x. Now I have an equation with, and you're going to get to your 2 eventually here. Okay, so I need to continue. So I'm still within this same idea here. So x is equal to y. And now on equation 3, we get x squared plus, x cubed plus x cubed must equal 16. That's 2x cubed equals 16. That's x cubed is 8. So x is 2. And if that's what x is, we already said that y must be the same thing, right? So I only have one critical point so far, 2, 2. Are there any others? I mean, shoot, we've looked at everything, haven't we? Have we looked at everything? We've said, what if both x and y are both 0? And we said, nope, that can't happen. We said, what if one of them is 0? And we said, no, that can't happen. And then we said, okay, well, what if neither one of them are 0? And the only answer we got was 2 and 2. Are there any other combinations you can think of? What if lambda is 0? Did we already consider that? Yeah, we said if lambda is 0, right? What happens? These equations can't be solved unless x and y are both 0, which we said we can't happen. Yes?
So we're supposed to always find something with Lagrange when we replace with a domain?
We should.
Always?
Yeah.
Because we have that third equation for like exists.
Yeah, think about if you have, if you have a constraint, okay? If you have a constraint, then there's some curve that lives on the ground, right? And then you have a surface above it. If you plug only these points into that surface, you have like this weird loop, rubber band up here somewhere. That should have a highest and lowest point. It could be constant where the highest and lowest point are always the same point, but you should have a highest and lowest.
There's not a point where it doesn't exist. So like, for example, in the original solid, like, there's like an asymptote. We have like certain.
Yeah, we would need it to be, yeah, we have to make sure that we're within the domain of the original function. If your restriction cuts through the domain, you have a problem. Look at this one right here. Look at your f of x, y. How are we doing on time? Okay. Look at your f of x, y there. You do have a domain restriction on that, don't you? I mean, you can't plug in 0 for x or y, right? That's automatic to begin the problem. X and y can't be 0. And so, same with the constraint, right? The constraint, you can't let x and y be 0. Might be helpful, I don't know. Just remember that f of x, y, if you wanted to rewrite that, could be rewritten as x to the negative 1 plus y to the negative 1. And the g of x, y could be rewritten as x to the negative 2 plus y to the negative 2, right? I mean, that's just another way to look at those two, so that when we take derivatives, it might be a little bit easier. Yeah? Okay, equation 1, doing Lagrange. Partial of f with respect to y must equal lambda times partial of g with respect to, wait a minute, I think I said the wrong thing. Partial of f with respect to x must be equal to lambda times partial of g with respect to x. Equation 2, the partial of f with respect to y must equal lambda times partial of g with respect to y. And then equation 3 is the constraint. 1 over x squared plus 1 over y squared must equal 1. Now, we are getting to a point where we're actually going to see how we could use these for a word problem. Like, remember I ended the class last time and I gave you the box within the ellipsoid or something like that? These are basically optimization problems. So we're just kind of making sure we know how to mechanically do it first. And then when we get to a word problem, we are going to convert something we're trying to optimize and then some constraint for that optimization. Partial of f with respect to x is
1 over x squared?
negative 1 over x squared, right?
Yeah.
Okay, negative 1 over x squared. And then lambda times, now the partial of this with respect to x would be negative 2 over x cubed. Negative 2 over x cubed, yeah, because we subtract 1. You okay with those derivatives? All right, then partial with respect to y is pretty much the same thing, right, with y's? 1 over y squared, negative 1 over y squared equals lambda times negative 2 over y cubed. And then we just leave the constraint equation. All right, we got to find x, y, and lambda that make all those true. I'm going to do first things first. Let's do this. So what did I do here? No, sorry. What did I do there? So I multiply both sides, right, by x cubed, right? Am I allowed to do that? Why am I allowed to do that? Do I have to say suppose like x is not 0? There's a domain restriction to begin with. We know x can't be 0, right? So I know I'm allowed to do that. Okay, I don't need to state it because it's not a case, it's not a special scenario. It is the domain allows me to do that, right? So I multiply both sides by x cubed. I also multiply both sides by negative 1, and it just got rid of it. Okay, so we good there? This one, same thing, right? Same thing, because y can't be 0 as well from the domain. So I know that y equals 2 lambda. Oh man, could this have been any cleaner? Wow. So why don't we solve each of these? I don't know. I mean, we have choice. I could just go into my last equation, just replace x and y both with 2 lambda, right? Couldn't I do that? All right, so I'm just going to do that. I don't even have to suppose anything right now, right? I'm not like saying, act like, x can't be 0. I'm just going to go right into equation 3 right now. Equation 3 now becomes 1 over 2 lambda, that squared, plus 1 over 2 lambda, that squared must equal 1. And now square everything. 1 over 4 lambda squared plus 1 over 4 lambda squared must equal 1. Those already have a common denominator. So put them together, I get 2 of those over 4. So 1 over 2 lambda squared equals 1. I just reduced the fraction. And then, okay. 1/2 equals lambda squared, multiplying both sides by lambda squared, and then take our square root on both sides. So lambda is plus or minus the square root of 1/2, or however you want to write that. Lambda is plus or minus 1 over root 2, and if you rationalize the denominator, you get root 2 over 2. That really doesn't care. That really doesn't matter. I don't care what you do with that, but. So now we can get x and y, can't we? Because I know what lambda has to be. Continuing my work here. So equation 1 now tells me that x is equal to 2 times lambda, right? So lambda can be, let's do it this way. Hold on. I'm going to do it this way. I have 2 different scenarios for lambda right now, right? I'm going to look at each one separately. So suppose lambda is the positive one. I don't require y'all to rationalize, but I'm going to in this case, all right? Because I know I'm going to multiply this by 2, right, over here, and the 2's will cancel. So I think it'd be cleaner if I rationalize. So I'm taking the positive of this first. If I do that, then equation 1 tells me that x is 2 times root 2 over 2, which is just root 2. And then equation 2 tells me that y is also the same thing, root 2. All right, just replacing lambda with root 2 over 2. So I have one of my critical points. Yes?
Could we not have also set x and y equal to each other?
When?
Once we saw that x was equal to 2 lambda and y was equal to
Yes.
2 lambda?
Yeah.
Okay.
And then you replace one of these with y or x. Yeah.
Okay.
So that's why I'm saying there's going to be some diversity within what each of you do, as long as you're not skipping anything or like saying, oh yeah, x can't be 0. You have to state these things. It's not assumed. All right. Now we suppose lambda is the negative of that. I'll do that up here. We're almost done with this one. Suppose that lambda is the negative root 2 over 2, then I'm not going to show all the work. This will be negative root 2, and this will be negative root 2 as well. So we get negative root 2, root 2, negative root 2. You know what I haven't done is plug those in, have I? Did I do that in the last problem? I feel like I'd never plugged them in. Did I? In our last problem, did I plug in? Didn't we only have one critical number? It was 2, 2, right? It was 2, 2. What I didn't do, oh shoot, I needed to go back. I need to go back and look at that. Let me finish this one up. Yeah, we need to talk about it. Is that a max or a min? See, it's hard to tell because you only have one number, right? Let me get back to it. Let's finish this one out. If you plug these in, I'm going to go ahead and just tell you what the answer is. If you plug in root 2 into the original function, you actually get root 2. If you plug in negative root 2, you get negative root 2. So this is our max and that's your min. I'm not going to show that work. Okay?
You have them both labeled as maxes.
What are you talking about? What? What were you saying? The what? What?
Sorry, it's old glasses. I must be blind.
Yeah, just clean them. Clean them with a paper, something. Yeah.
Check the video later.
If that video gets uploaded. No, thank you. All right. Okay, got it? This one's done? Yes? Now, let me go back to this one because I didn't say something I should have, and I just got distracted with my own thoughts here. So back on this one, right, we had a critical point, and we only had one answer, right? 2, 2? That was it. So if I plug 2, 2 back in this one, if you plug 2, 2 in there, you get e to the 4th, right? 2 times 2 is 4. E to the 4th. The problem here is I don't know if that's a maximum or a minimum, right? How would I ever know that? Understand? So here's what you have to do. It's either a max or a min. So what I can do to determine which one it is I can find any x, any y that make this constraint true. Plug that into here and see if it's bigger or smaller than this. If it's bigger than this, then this has to be the minimum. If it's smaller, then this has to be the maximum. Because this is either a min or a max. So looking at this equation right here, can we come up with a number that would satisfy, an x and a y that would satisfy that? How about this? X is 0, and y is the cube root of 16. If x is 0 and y is the cube root of 16, then what's the cube root of 16 cubed? 16, right? So do you all agree that this point right here satisfies the constraint? Right? That satisfies the constraint. Now take that and plug it into this. What would happen if you replace x with 0 and y with cube root of 16? You get e to the 0, which is 1. What's bigger, e to the 4th or 1? E to the 4th. That means that has to be a maximum. Make sense? You only have to check one point. I already know that's either a max or a min. So I'm comparing it to some other point on the constraint. If this is bigger than that, then it's a max. If it's smaller, it's a min. Can't believe I overlooked that. Well, I believe it, but. Okay, you all right? So far, everything's been okay?
It's all right.
So what we've been doing up to this point is we've been looking at a surface, right? Restricting the domain to a curve on the ground, plugging those points in to this weird rubber band on the surface, finding the highest and lowest points. Now, what we're going to do is our function is no longer going to be a function of 2 variables. It's going to be a function of 3 variables. So now, instead of having a surface where your domain is some curve on the ground, you have a function of 3 variables that you can't visualize, right? You can't see it anymore. And we're constraining it to a curve that lives in 3-dimensional space. So instead of the domain being on the ground being like a circle, you now have like a curve in 3-dimensional space. The points on that curve in 3-dimensional space are being plugged into a 4-dimensional function that you can't see, and we're trying to find the biggest and lowest values, or maximum and minimum values of that function that you can't see. that make sense? Yeah, it's kind of, right? Look, what we did right now, the domain, let me go back to the original one. This one right here. The domain of this, here was the original surface, right? There's your original surface, right? That's a function of two variables. It's a function of two variables, right? So there's your surface. We're restricting it, right? The constraint equation created a curve in two-dimensional space. Those points got mapped up into the function and created a curve on the function that we were trying to find the highest and lowest points of. Now, your curve is no longer on the ground. Your curve could very well be this curve right here, this blue curve. That's our domain, and those points are being plugged into a function that takes in x, y, and z and spits out a fourth value. You can't visualize it anymore, but we can still say where is it the biggest and where is it the smallest. In other words, this whole idea of Lagrange extends into whatever dimension you want. Okay, whatever dimension. You can have a function of two variables constrained to a domain that lives in two-dimensional space, or you can have a function of three variables that lives in four-dimensional space and have the domain restricted to 3 dimensions. Yes, 3 dimensions. Or you could have a function of 4 variables which lives in 5-dimensional space, your constraints in 4-dimensional space. Or just keep going, right? Yes?
Does that mean we have to have like 10 equations?
Yes. That means you're going to have more equations to solve. So now we extend the Lagrange. Lagrange multipliers, 3 variables. This is as far as we go in Cal 3. As far as we go is 3 variables. But in theory, you could extend this to 4, 5, 6, 7, and variables. Right? That's what's so powerful about Lagrange is that you can take any function that takes in, however many variables, weather forecast, something like that, and you could constrain that to certain inputs, and then you could find max and mins. Yes?
I was going to say, as I said, the majority of the stuff that we do is where we can add more variables.
Yeah, in the real world, we have lots of variables with, not always 2 and 3. Okay, well, it's the same exact idea. You have a function now of 3 variables. You have a constraint equation that has 3 variables equal to a constant. You still want to figure out where the gradient vectors are parallel. And you still want to make sure that the constraint equation is satisfied. The big difference is that when you do these gradients, you now have the partial with respect to x, partial with respect to y, partial with respect to z, right? You have 3 things. So now you're going to come up and have 4 equations. This one, this one, this one, this one. So you have to find out the x, the y, the z, and the lambda that make all 4 equations true simultaneously. Solving 3 equations and 3 unknowns has been already a little bit, now we get 4 equations, 4 unknowns, and this is where the algebra starts to get fun. Let's try this one. We have 10 minutes. Let's see if we can get through this one. This is a pretty clean one, I think, because look at the f of x, y, z.
Yeah.
It's a pretty simple equation. So let's at least see if we can set this one up properly. So how do I know it's Lagrange? Function of 3 variables, right? Constraint equation, 3 variables equal to a constant. So I'm going to do Lagrange. Equation 1. Partial of f with respect to x must be equal to lambda partial g with respect to x. Equation 2. Partial of f with respect to y must equal lambda times partial g with respect to y. Equation 3. Partial of f with respect to z must equal lambda times partial g with respect to z. And then finally, equation 4 is our constraint equation. X squared plus 10y squared plus z squared must equal 5. Partials. Partial of f with respect to x is just 8. Nice. Lambda, partial of g with respect to x is 2x. Okay, partial of f with respect to y is what? 0, right? There is no y in my f function. 0 equals lambda, partial of g with respect to y, 20y? Partial of f with respect to z, bless you, -4. And then equals lambda, and then times 2z. That good? Shit. We have a lot of things we got to look at here, right? There's a lot going on here. Anything I can clean up? I'm going to clean up whatever I can. Like, I'm going to divide both sides by 2. I mean, like, I'm really hoping I can make this as nice as possible. Can I divide both sides by 20 here? I can, right? 0 equals lambda times y. Here I can divide both sides by 2 again. Negative 2 equals lambda z. And then I'm not going to touch the constraint. That's just me trying my best to just clean up a little bit, so throw away stuff I don't need. Lambda can't be 0. I agree. Lambda can't be 0. If lambda is, well, it can be 0 here, but it can't be 0 everywhere, right? Yeah. So we can say that, lambda can't be 0. All right, I think that's a good way to start. Suppose lambda isn't 0. Now what?
Then use y must be 0?
For x.
We will, well, yeah, what, if lambda's not 0 and this is true, then forces y to be 0. That's what you're saying, yes.
That's what I mean.
Let's go through each one of these, though. I'm going to get to that. What about here first? If lambda's not 0, what do you want to do?
Then x equals 4 over lambda.
You could solve for x here, right? And couldn't you solve this for z? Divide through by lambda? So you would have x would be in terms of lambda, z would be in terms of lambda, right? And if that's in terms of lambda, that's in terms of lambda. This is almost all in terms of lambda. But if lambda is not 0 and you divide through, then that would force y to be 0. So you get rid of the y there, wouldn't you? All right, this is looking pretty good, actually. Okay, so suppose lambda is not 0. Then equation 1 tells us that x is equal to 4 over lambda. Equation 2 is telling us what? Y has to be 0. Does anyone have a question on why that's true? Everyone understand that? We're good? Equation 3, what's equation 3 telling us? Z is negative 2 over lambda. And now I can use all that information to go to equation 4. Equation 4, x squared, x for us is 4 over lambda, 4 over lambda squared plus 10 times y squared, but y we just said was 0, plus z, which is negative 2 over lambda squared, must equal 5. Square, 16 over lambda squared plus 4 over lambda squared equals 5. 20? Yeah. So 24 is, what's lambda? Plus or minus 2? Can I just go to it, or yes? Lambda is plus or minus 2? So let's now look at both of those scenarios. We're still within this same big suppose. So let's indent and do a new suppose. Suppose that the lambda is 2. If lambda is 2, what's x? Then x must be 2, right? 4 over lambda. And then the y we already said was 0, right? And then the z must be negative 1. Yeah, if it's positive 2. Everyone got that? Mm-hmm. If lambda is positive 2, we get 2 here, we get negative 1 there, and then y was 0 to begin with. And now the other suppose is that lambda is negative 2, and that makes my x negative 2, my y is still 0, and my z now is positive 1. Okay, I have 2 critical points, don't I? I have 2, 0, negative 1, 2, 0, negative 1, and then the other point is negative 2, 0, positive 1. What I know so far, well, let me see, have we covered all the cases? Have we taken care of every scenario? We said that lambda couldn't be 0, right? So we already said if lambda is 0, we can't satisfy which one? This one, right? So lambda can't be 0. So when lambda is not 0, it's that. Any other things? What? Can x be 0? X can't be 0. This isn't true. Can z be 0? No. Can y be 0? Uh-oh. But we already said it is, right? So we don't need to think about it. But I'm just rethinking through everything, making sure we covered everything, right? All right. So now what we do is we take those two values, or those ordered triples, and we plug them into here, and we see which one gives us the biggest and which one gives us the smallest. Unfortunately, I cannot show you a picture of this. I can't graph this thing for you. I can just tell you that the biggest that this function will ever be, if you constrain it here, is one of those two. It's the first one, top one, yeah. 16, 20? 20, yeah, 20, and then the other one is negative 20. 20 and negative 20. All right, so we are, we have a test on Wednesday, don't we?
Yeah.
Okay, this will not be on there. All right, I think we'll stop. We don't have time for another question or another problem. We have a few more minutes. Any questions about the exam? What's the expectation for those of you who may not have been here and didn't watch the video? What are we doing on Wednesday? Test? You can bring what?
You can bring the formula sheets under the formula section.
You can bring the formula sheets.
Bring one 8.5 by 11 front side.
Yes, so you have the formula sheets that you're allowed to bring from Canvas, nothing more, not edited, your own version of it with writing all over it. The formulas from Canvas. And then you can have one reference sheet, right? 8.5 by 11, front and back, steps, formulas, procedures, no worked out problems, right? No worked out problems. Also on that, you can, if you want a unit circle, put it on your reference sheet, right? Or something like that. Anything that you want addition, you can't bring in a separate sheet. It's either got to be your reference sheet, you put it on there, or you don't have it at all. Any questions on the problems or anything? I think I gave you all an outline, right? I told you. I just went through the test and I said, these are the things you need to know. I was asked earlier about, the quadratic surfaces? That day we looked at all those surfaces. We said, oh, this is a hyperloid of two sheets and all that stuff. Ellipsoid, cone, all that. You do not need to be able to look at a formula and identify which it is. That's not something I'm going to test you on. What you will have to do is be able to find the center of a quadratic surface by completing the square. Were there any other questions over? Yeah?
I have a question about the last mini exam.
We can talk about it.
Yeah.
Any other general questions? Yes?
You said no surprises, so don't bother studying all the other stuff. You've been just what you
Yeah, if I did not mention it on that